There we go. It's taken me a minute to look at my notes and see where we're making the substitution. Okay, go back to your definition for Ka of your acid and notice that HA over A minus equals H3O plus divided by Ka for my acid. Do you see how we can get from there to there? It's just a little bit of algebra. Okay, so then we can actually adjust our expression for the concentration of RH plus, and that's going to equal simply H3O plus times the concentration of R divided by the Ka for my acid. And then if I put that into my rate expression, the rate law for formation of product here depends on some rate constant, some equilibrium constant, the concentration of R, the concentration of H3O plus, and then my acid dissociation constant. So even when, and it's, presumably this is an aqueous solution, but even when it's not H3O plus doing the protonating in aqueous solution, the rate still only depends on the pH, which is kind of a weird and counterintuitive conclusion. The rate for this reaction will depend on pH, it will depend on the acid dissociation constant, and then it will depend on the equilibrium constant for this reaction. And so again, if your acid does the protonating before the rate determining step, adding more acid actually isn't going to help you. That makes intuitive sense even if you're not following the math. If the protonation is not the rate determining step, if something else is slower, it doesn't matter if you're going faster, if you supply more acid to go faster, right? Because the rate is determined by the subsequent step. The analogy was years ago we were making a ton of lunches for some purpose, and it became very clear that I was the rate determining step, so it didn't actually matter how fast somebody was painting peanut butter on a sheet of bread or slice of bread or putting jam there or slapping it together, because I was so slow getting it in the bag. I became the rate determining step, and increasing the rate of making the sandwich really didn't help at that point. You gotta, okay, so that's specific acid catalysis. And if you don't remember anything else about specific acid catalysis, this is a situation where you need to protonate first and then you do the reaction, okay? So an example of something like that might be acetal formation chemistry, where suppose I want to make the acetal of this ketone. Methanol is not really a strong enough nucleophile to attack directly, so likely what happens is in a pre-equilibrium step, I get a proton from some source. Who knows? It might be the specific acid, which is the protonated form of the solvent, or it could be an acid that I add. But this would be an equilibrium step where first I protonate the ketone and then in a rate determining step, and I'm not sure, there's a lot of steps in acetal formation, so I'm not sure which one is the rate determining step versus not. But I'm guessing that of all the steps that are possible, this one might be the slow one. In any case, this is an example of specific acid catalysis, or at least the way you've been taught to draw this mechanism is an example of specific acid catalyst, because you've got an equilibrium that's prior to the rate determining step. Okay. So, with that in mind, what on earth is general acid catalysis? General acid catalysis, ironically, involves using an acid that you add to do the protonation during the rate determining step. All right, and that'll be our key feature of general acid catalysis, is you have proton transfer during the rate determining step, RDS. So this might involve what are we doing here? Sorry, my notes are kind of funny. Okay. So this might involve some acid HA and some starting material R and then water. And in the same slow step, you protonate your starting material and you have water add to it. Think of this like ketone hydration as an example, with the conjugate base of your acid, and then you've got subsequent fast conversion to your product, whatever it is, and reformation of your acid. And this is a feature of both specific acid and general acid catalysis. You got to regenerate the acid before the end. So the rate of formation of the product here is going to depend on some rate constant times the concentration of acid times the concentration of your starting material. I'm not including the concentration of water because it is huge and unchanging, and so we'll just fold it into the rate constant K. Like pure water is 55 molar, and usually organic reactions occur on the millimolar concentration scale. Okay. Sorry. So in this case, what you would see, because the acid concentration itself is in the rate law, you would see that as I increase acid concentration, the rate goes up. So if I were to do, again, initial rate type analysis where I started with different concentrations of R and I measured the rate just at the very beginning and then measured an observed rate constant and plotted that versus R, I would see the rate increase as I increase the concentration of my acid. Now, how would the rate depend on pH? This is actually interesting. If I change the pH, at first it's not going to matter until I get to a pH that's about the pKa of my acid. If the acid's involved in the rate determining step, changing pH won't matter as long as I have enough of that HA present. But as I get near as my pH gets close to the pKa of the acid, I'm going to see the rate drop off precipitously. And this point will be sort of the pKa of my acid. Do you remember how we said when pH is greater than pKa, that the conjugate base form dominates. That's a formulation of the Henderson-Hasselbach principle. All that means is the reaction rate goes way down once my pH is high enough that I don't actually have a lot of HA present. You can, and another way to write this, I mean, you can use the definition of Ka for your acid. HA plus water goes to H3O plus and A minus. And you can write Ka equals concentration of H3O plus times concentration of A minus divided by concentration of HA. And you can substitute that into this equation, K times H3O plus times A minus times R divided by Ka. And as you look at that, you might say, whoa, that looks a lot like the expression for general or for specific acid catalysis. You have a term in there that's sort of like pH, and you said that up to a certain point pH doesn't impact the reaction. Compare these two rate laws. Compare this to this. Aside from the constants, what's different? H3O and R both appear there. What isn't here that is here? Does that say louder?
Well, the KEQ is in the first one.
Right, KEQ is here. Are there any concentration terms that are present here or here that aren't in the other? Yeah, that A minus. What that tells you, the lack of a concentration of conjugate base up here tells you the equilibrium between acid and conjugate base doesn't matter. It's only the pH that matters. Whereas here for general acid catalysis, that equilibrium does matter. And so as you increase pH, you're good to a point, but once your pH gets beyond the pKa of your acid, you no longer have enough HA to catalyze the reaction. Okay, so the big take home, and if you only remember one thing from general acid catalysis, it's that the acid is involved in the rate determining step. So an example of this, and I'm not trying to say whether the mechanism's one way or another, but consider like ketone hydration, and consider if this were the slow step, right? If the water attacked the ketone at the same time as lone pairs on the ketone attacked an acid. Put proton transfer together all in one concerted step, and that would take you directly to this intermediate, this oxonium ion. And then suppose that the remainder of this is fast, where the conjugate base of our acid would remove a proton, and then we get the ketone hydrate and our acid regenerated. Now I'm not actually saying, because I don't know whether if you do the kinetic analysis for this particular reaction, whether it is general versus specific acid and base. But now you have some tools to test whether that's the case. In the examples shown here, the proton transfer occurs during the rate determining step. In the example above, the proton transfer occurs before the rate determining step. And those have specific consequences in terms of what accelerates the reaction and what doesn't. Yeah?
Is there a way that you can tell just from like reactions given which one it's going to be, or do we have to do the kinetic experiment?
That's a great question. Can you tell based on what the reactants are whether the reaction's going to be one versus the other, or do you have to do the experiment? I think you have to do the experiment because those two examples I gave you, I couldn't tell you why I predict this to be one or this to be the other. And in fact, as I said, I don't actually know whether these reactions that I've shown you are specific versus general acid catalyzed. I gave you an example of what it would look like if it were. Frankly, by the time I start drawing mechanisms in my second semester OChem class for mechanisms for metabolism, I get so sick of drawing proton transfers as their own steps that I just sort of do this. And that's okay for shorthand. But you should remember there is a way to figure out whether that proton transfer occurs at the same time as the rate determining step or after. And it's you try increasing the acid concentration. If the rate doesn't change, that's specific acid catalysis. If it does change, that's general acid catalysis. You see if I control pH and then increase it, what does that do to my rate? For specific acid catalysis, lowering pH should increase your rate. For general acid catalysis, lowering pH does nothing. Increasing pH beyond the pKa of the acid that you add causes the rate to drop off.
So, do you know of any examples where it really matters if you're getting the same product between the two?
Right. Does it even matter if you're getting the same product from either one? Probably not. Though from a practical standpoint and from an engineering standpoint, I think it would matter, because then the steps you take to accelerate the reaction are different. If I know that it's specific acid catalysis, then I'm not going to worry about increasing the concentration of my catalyst. All right. So drawn some energy diagrams here, but this was last year, and I'm trying to look and see whether I think it's significant enough to talk about. Maybe. So consider, we're talking about addition to a carbonyl. Consider some nucleophile and you've got some carbonyl compound and you've got some acid, and you want to go to the addition product with your nucleophile here, and then I guess the conjugate base of your acid. If there's no catalysis and we do a reaction coordinate energy diagram with energy on this axis and then reaction progress or reaction coordinate on this axis, the uncatalyzed reaction looks like this. The proton transfer doesn't happen prior to the rate determining step or even during the rate determining step. You have the nucleophile and the ketone, and you make the addition product, and then in a subsequent fast step you protonate and go to product. So this is what it would look like if there was no catalysis. And in fact, it's not catalysis because the acid isn't regenerated, right? So that's how would then catalysis change this picture. You could imagine specific acid catalysis, and in this case you would do proton transfer prior to the rate determining step. What would this look like? Well, you would have your carbonyl compound and you'd have the acid HA. I'm going to zoom in and it's a thinner line. And I am very sorry. I'm trying to sort of draw things on roughly the same scale, and it's not working very well. So you start out at the same point, but prior to the reaction, you protonate the carbonyl compound, and this isn't the rate determining step, and you can tell it's not the rate determining step because it's not got the highest activation energy. And then the nucleophile attacks, and maybe once the nucleophile attacks, you get some intermediate like this. And then there would be another step where you would regenerate your acid. Usually, in such circumstances like this, the nucleophile would maybe have a proton that could be removed to regenerate your acid. Okay? And how does this accelerate things? Well, relative to where we were, we've lowered the energy of the transition state. Okay? In contrast, general acid catalysis would involve here my nucleophile, the acid, and the ketone, and there would be some concerted transition state, and in the product, and then I would go straight to products and having regenerated my acid. And the transition state might look something like this, where the nucleophile is coming in at the same time as I'm transferring a proton from my acid. All right, I think that's probably enough on that particular thing. Anything you want to ask there? I just think it's useful to think of, because at least if you think about enzymes and what's going on in chemistry, in biology, we often think, okay, well, the enzyme takes care of the proton transfer. But actually, when and how that proton gets transferred is a little challenging, and so it's useful to know whether the reaction, whether the proton transfer happens before or during or after the rate determining step. And some of this may influence enzyme evolution. If there's a particular reaction that is general acid catalyzed, then yeah, improving the enzyme, improving the acid in the enzyme should really help. If it's specific acid catalyzed, not so much. And so there may be different strategies for enzymes to catalyze these reactions. All right, speaking of enzymes, our last thing I think in this chapter is going to be Michaelis-Menten Enzyme Kinetics. And this you probably got in biochemistry. Though if you read the literature, especially if you're interested in medicinal chemistry and developing inhibitors of enzymes, inhibitors of kinases, it's useful to know your way around the Michaelis-Menten equation, and useful to know what Kcat and Km are and what they really describe. So Michaelis-Menten kinetics, I don't know why we pronounce Michaelis like that, but we pronounce Dr. Michaelis, Dr. Michaelis. I don't know. But if you want to tick him off, maybe you call him Dr. Michaelis. And you can tell him I said that. We're friends. In fact, both he and I were grad students together at the University of Wisconsin. He was maybe one year younger than me, and he was way smarter and way better at chemistry. And so I was glad that when I interviewed for this job, he wasn't on the market at the same time I was, because not sure how it would have turned out otherwise. Okay, so Michaelis-Menten kinetics involves a fast equilibrium binding of enzyme to substrate, and there's some forward rate and some reverse rate. And then let's say this is the rate determining step, and this is the conversion of the enzyme substrate complex to the enzyme product complex. ES stands for enzyme substrate complex. EP stands for enzyme product complex, and then you have fast dissociation to give the enzyme and the product. So All we care about is the stuff that happens prior to the rate determining step. And we will say that the rate constant for conversion of the enzyme substrate complex to the enzyme product complex is something called Kcat. It's a unimolecular rate constant, the rate of catalysis. And so the appearance of our product should be equal to the Kcat rate constant times the concentration of the enzyme substrate complex, which we don't know. And because the enzyme is a catalyst and presumably is not present in very high concentration, we can use the steady state approximation to solve for the concentration of the enzyme substrate complex in terms of things that we do know or that we can know. So remember, the steady state approximation is to say that the enzyme substrate complex, the rate of change in the concentration of the enzyme substrate complex is 0. So what causes the enzyme substrate complex to form? That would be this K1 forward rate term times enzyme concentration times substrate concentration. Then disappearance of enzyme substrate complex would be this K-1 term, just the dissociation of enzyme and substrate. And then also the catalytic term, forward reaction of the enzyme substrate complex to give product. Now, this is a little bit tricky because, as I said, E is free enzyme, ES is bound enzyme. We may not know either of those at any given time, but we do know what the total enzyme concentration is. And we know that overall that needs to remain constant as a function of the reaction. Total concentration of enzyme, which we'll call E with the 0 on it, should equal the concentration of free enzyme plus the concentration of bound enzyme, because that's all the enzyme that we have. Now, there's going to be just a little bit of algebra, which you are going to hate, and it's okay. We're going to, every time we see E, we're going to substitute in E0, the total enzyme concentration, minus ES. Because remember, we want to substitute ES and solve for this rate. We can't do that yet when we have E present. So fortunately, we can write the amount of free enzyme as the amount of total enzyme minus the amount of ES. So with that in mind, here's our new equation, K1 times E0 minus ES times the concentration of S minus K minus 1 ES minus K cat ES. Right. And then what we're going to do is some algebra to get all of the ES containing terms on one side of the equation and all of the terms that don't contain ES on the other side of the equation. What this is going to look like is concentration of enzyme substrate complex times K1 times the S concentration plus K minus 1 plus K cat. And on the other side of the equation, we're going to have K1 times the total concentration of enzyme times the concentration of substrate, such that the concentration of ES equals this. And then we can just put all of that into our expression for the rate and write a new rate law. And that's going to be complicated enough, but we can't really leave well enough alone. And we're going to make it a little bit worse. Kcat times K1 times enzyme total concentration times substrate concentration divided by K1 times S plus K minus 1 plus Kcat. All right, I'm going to just pause there. We can take a breath. We can look at it. Any questions so far about the algebra? This is just, we're just following through the consequences of the steady state approximation. Now, what we're going to do at this point is we've got K1 here and here in the numerator and the denominator except for here. So what we're going to do is we're going to multiply the numerator and the denominator by 1 over K1, which is just like multiplying by 1, so that's allowed. We get rid of K1 in the numerator. We get rid of K1 here. But what's left over is we have to have these last two terms divided by K1. So in parentheses, I'm going to have K minus 1 plus Kcat divided by K1. And this is what we're going to define as the Michaelis constant Km. Big Km, which is K minus 1 plus Kcat divided by K1. This is the so-called Michaelis constant. Now, if we look at what units the Michaelis constant is going to have, let's look at what the K minus 1 term is from our equilibrium expression. The K minus 1 term should have units of per second, because remember rates need to be in terms of moles or change in molar per second. The rate law for this backward step is K minus 1 times the concentration of ES, and that's in molar. So in order to get the rate in molar per second, the K constant only, K minus 1 only needs to be per second. Is that, you get that? In contrast, K1 has to be per molar per second, because in the rate law for this forward step, you have two concentration terms, and to end up with a rate that's not molar squared per second, the rate constant needs to be per molar per second. Similarly, for similar reasons, Kcat is going to just be a unimolecular rate constant in per second. So if we bring that down here and look at what the units of Km are, K minus 1 is per second, Kcat is per second, K1 is per molar per second. All of the per seconds cancel each other out, and the units of Km are molar. So Km has the same units as a dissociation constant. Have we ever talked about binding? Have we talked about dissociation constants before? I don't remember. Okay. So just a little bit of background there. If you have molecule A and molecule B, and they come together and form complex AB, you can write about this equilibrium in a couple of ways. You can write an association constant, which is the forward direction where the product is AB and the starting materials are A and B, or you can write it in terms of the backwards reaction where AB dissociates to give you the complex between A and B dissociates to give you A and B. And in that case, KD equals concentration of A times concentration of B divided by AB. And you can see that the units of the dissociation constant should just be molar, some kind of concentration units, right? Whereas the units of the association constant should be per molar. So the Km is in units of molar, and so some people like to think of the Km as being related to some kind of binding. You can think of Kd here as the concentration where you would have 50-50 bound and unbound starting materials versus products. Just to give you a sense for what these numbers mean, with Kd, lower numbers mean stronger binding, right? Because it's a dissociation constant. And association constant, higher numbers mean tighter binding. So as an example, if my KD for one, suppose I have many different suppose I have many different molecules B that bind to protein A or something like that. If the KD for the AB complex equals 10 micromolar, whereas the KD for some other B complex equals 10 nanomolar, that means this one is the more stable complex. This one's tighter. Typically, when we talk about dissociation constants in organic chemistry and in biology, we will use the millimolar, micromolar, nanomolar, picomolar units. 10 micromolar is 3 orders of magnitude higher than 10 nanomolar, which is 3 orders of magnitude higher than picomolar. In order to be generally for complexes that form via non-covalent interactions, micromolar binding constants are pretty uninteresting. And there's a whole long history of chemists trying to design molecules that bind other molecules. I talked about some of the macrocycles, crown ethers that bind cations in my seminar earlier this semester. And for a lot of those systems, the binding constants or the dissociation constants are in the micromolar range, which was a great achievement then. But a lot of the binding constants between enzymes and substrates physiologically are in the nanomolar range or lower. So if you're trying to design an inhibitor of some kind of enzyme substrate interaction and all you're getting are micromolar binding constants, probably you need to try some other approach. I was at least trained to hear, in most cases, if the binding constant is micromolar, you sort of yawn and say, okay, what else you got? Because that's not, something that has that kind of binding constant is not likely to be a drug. Okay, one other thing about dissociation constants, you have a rate for binding, which is K on, and you have a rate for dissociation, which is K off. And the binding constant Kd is going to equal K off divided by K on. So one way you can have a really good binding constant is to have a really, really slow off rate. That means when things bind together, they don't come apart very fast. The other way you can have a really great dissociation constant is if the on rate is super fast. So remember, lower Kd numbers mean stronger binding. So you got two ways to lower Kd. You can make binding faster or you can make dissociation slower. All right. With all of that in mind, let's go back up to that equation that we wrote. Oh, what a mess of stuff, huh? And let's try to figure out what some of these terms mean for the Michaelis-Menten equation. Because we're going to rewrite that as the rate of appearance of my product equals Kcat times the concentration of enzyme times the concentration of substrate divided by the concentration of enzyme plus Km, where Km equals K minus 1 plus Kcat divided by K1. Now, if I were to say what is the dissociation constant for the enzyme substrate complex going to just enzyme and substrate, that would equal the off rate, K minus 1, divided by, the off rate, K minus 1, divided by the on rate, K1. Do you see how that might be the dissociation constant for the enzyme substrate thing? Okay. Sometimes people like to interpret Km as though it were Kd. I want you to compare those two equations and tell me in what situations might I be able to say that Km resembled this dissociation constant. What would have to be true for that to be the case? So, okay, right, if it's not a catalyst at all. Yeah, and I guess what you're saying is if Kcat is really low, or in other words, if K minus 1 is much greater than Kcat, then Km is pretty similar to Kd. All right? That's true, as you said, that is true when the enzyme isn't that good. In contrast, for really great enzymes, you would want Kcat to be much, much greater than K minus 1. Because remember, K minus 1 is the unbinding rate, right? So it's a terrible enzyme if, as soon as you bind, you fall apart before you can go on and do the reaction. And if Kcat is much, much bigger than K minus 1, then your Michaelis constant actually has nothing to do with binding. It's really Kcat over K1. It's not a dissociation constant, but it describes whether the enzyme is good. All right, so we need to leave it there, but we'll pick up next time and talk just a few more things about enzyme kinetics. We need to talk about saturation and so on. So see you next time.